All right, so good day. I would like to thank the organizers, especially Professor Ming Fa Lin of NCKU for giving me this opportunity uh, to make this presentation at this international conference, which deals with emergent materials and batteries. This work was done in collaboration with two of my colleagues, um, Professor Andrei Huroff of Medgavis College of the City University of New York, as well as Dr. Dan Hong Wang, who is at the Air Force Research Labs in Albuquerque. The title of the talk is Klein tunneling of optically tunable Dirac particles with elliptical um, symmetry. The brief outline of the talk is as follows, namely, I'll give you a little overview of some of the materials which we have been doing here at City University and in collaboration with the Air Force Research Labs. They include, but not limited to, TMDCs, as well as alpha T3. The, the, the alpha T3 material or DICE model is the material which I'll be concentrating on, being given this limited time that I have today. What I will do is to present uh, a short summary of the formalism which is used to consider in doing our calculations. And then I'll turn to the Klein tunneling as an example of some of its applications. As I said, we have been involved in many materials. Some of them are listed here. They're buccal structures, such as silicene, germanine, tinine, the TMDCs, as well as phosphorine. But today, I will be presenting some work on a material which is related, quite similar to graphene, with a honeycomb hexagonal structure. Now, as you know, graphene has a honeycomb lattice, which consists of two interpenetrating lattices with A and B atoms. And here I'm showing the lattice structure where we have the A and B atoms. And the electrons, these fermionic atoms, allow electrons to hop around the perimeter of the hexagon with some hopping parameter T. As a result of this, one obtains two cones. One is a conduction band, and the other, the valence band. The main thing to notice here is that they touch. So which means that graphene is not a very good candidate as a semiconductor. Let us now turn to the alpha T3 model, where we have the A and B lattice, sublattices, as I mentioned, as occurs here in graphene, as well as a third sublattice, which consists of C atoms. Now, these C atoms are at the center of each hexagon, and you still have the hopping of the electrons around the perimeter with the hopping integral T. But in addition to that, you have a hopping which is allowed from the C atom to one, not both, of the atoms A or B. As a result of this, you have the following situation, namely you have the conduction and valence bands as you have in graphene, the two cones touching each other right at the Fermi energy for undoped graphene, as well as a flat band. Now the energies for the cones are going to be described by epsilon equal to h bar vf times k. So that's the cone structure, plus or minus. And so we label the plus or minus by the letter gamma. So we have here now introduced two parameters which we need to pay attention to. One is the alpha for the model, as well as this letter gamma, which labels the subbands. Now, just as a passing, I should say that the alpha T3 is named for this parameter alpha, as well as the 3 atoms ABC making up the lattice. So that gives you the alpha T3 model. Now, the energy bands could be obtained in a very straightforward way using the Dirac-Weil Hamiltonian, which I'm giving here on the left-hand side. And it involves a parameter phi, which is related to the parameter alpha in the following way, namely that the tangent of phi is equal to alpha. So far we have two parameters, or maybe three, which we need to be aware of in some of the work which I'm going to be describing here, namely gamma for the energy bands. So gamma is plus or minus 1 or 0 for the flat band, plus or minus for the conduction valence bands, as well as this parameter phi, where the tangent of phi is equal to alpha. Now this 3 by 3 matrix involves this wave vector k plus or k minus, here given in the first line after the equation, as well as a parameter gamma. Now this parameter gamma is a label for the values. So we have now the alpha for the model, gamma labeling the energy bands, and tau labeling the values. So we have the k or the k prime value, where the tau is equal to +1 for the k value, -1 for the k prime value. Now there are a couple of interesting things to note for this Dirac-Weil Hamiltonian. One is if I set phi equal to pi over 4, it reduces to the Hamiltonian on the right-hand side of the equation. And also if I set, so this is the dice lattice case, if I set phi equal to 0, then I eliminate both the third row and the third column. And you may recognize that in that case, when the phi is 0, I have this 2 by 2 matrix, which is exactly the Dirac model, which is the sigma.p model for the low energy subbands. The energies, as I said, are labeled by gamma. They're not labeled by tau. However, the wave functions are labeled, which are given here, for the conduction and valence bands, as well as for the flat band. They are labeled by the value index tau. So the values have the two values are degenerate in energies with different wave functions. It would be interesting to see what happens when you apply an external EM field. That is, what happens to the wave functions, what happens to the energy bands, and so forth. What we have done is the following, namely we apply this external EM field, which could be expressed in terms of a vector potential A. Now, this vector potential depends on the frequency of the external field, as well as the strength of the electric field, E0, and it could be not necessarily circularly polarized. So here is an extra parameter beta, where beta is the ratio of the semi-major axis to the the semi-minor axis to the semi-major axis of an ellipse. So the value of beta could vary between 0 and 1. In the case when the beta is equal to 1, we have circular polarization. And in the case when beta is equal to 0, we have linear polarization, as I described here in these two equations. The two cases of circular polarization and linear polarization are quite interesting in their own right, as I will explain. Recall that the um, original Hamiltonian, the Dirac-Weil Hamiltonian, depends linearly on the momentum. So here, when we apply an external field, we make this substitution or replacement. K or P is replaced by P minus EA, or K is replaced by E over H bar. When we do that, we end up with the following interesting situation, namely that the Hamiltonian is then replaced by a new Hamiltonian, which is time dependent because the vector potential depends on time. But here we can separate out the time independent part, which is just the original Hamiltonian, plus the time dependent part, which is given here in this equation. So we have now a new set of parameters to pay attention to. There is the coupling between the electron charge, the charged electrons, with the external field. And that's given in terms of the parameter C naught. So this C naught is going to, could be varied. That is the strength of the coupling, the strength of the interaction between of light with matter could be adjusted. That is, the C naught value could be changed. And here is the T dependent Hamiltonian. Okay, so let's see what we have. We started off with an originally time-independent Hamiltonian. We did this substitution and ended up with a time-dependent Hamiltonian. The time-independent part of the Hamiltonian gives us the eigenvalues, gave us the energy subbands. The question then is, what do we do with this Hamiltonian which depends on time? We are lucky in the sense for the following reason, namely that the this time-dependent part could be evaluated perturbatively using what's known as the Magnus-Fluke transformation or approximation. In that case, one should note that the frequency of the external beam, the omega, must be much larger than the corresponding energies which we are dealing with in the subband energies. So it must be off resonance from the energies which we have for the energy subbands. In doing so, after we made this transformation, then look what we have. We have, with application of the external field, we have, instead of two cones which touch, and those two cones, remember, the energy subbands, they have a flat band also. And they are, as I said, they are value degenerate. That is, there's no distinction between one value and the other. But here we find that, remember that if we take a cross-section of the cone, it's circular. However, that is isotropic, that is, the energy is isotropic in K space, is independent, it does not depend on the direction of the wave vector K. But here you see, we have the two subbands labeled by epsilon plus, epsilon minus. So I have the conduction and valence bands. And we have here, for the blue, we have KY dependent energy. For the red, we have, and the other color shows that we have a dependence on the KX. So we have broken the symmetry of the energy subbands. And the inset shows you that it's no longer circular. It's as if you take a cross-section of the energies. We no longer have a circular cross-section, but it's now elliptical. So that's why in the title of the talk, we have made mention of the elliptical properties of this of the material subbands when an external EM field is applied. Okay, now at k equal to 0, it's kind of interesting in the sense that for k equal to 0, we have the conduction and the valence bands. We have a separate, there is a gap between the two. So this clearly shows that there's an energy gap. The flat band in the presence of the EM field is no longer flat. It varies, and also it varies with the value of phi. That is the coupling parameter phi. And also remember I said that the phi is related to alpha. So alternatively, you can plot the behavior of the energy subbands at k equal to 0, not only as a function of phi, but also as a function of alpha, in order to get some illustration of how the band gap emerges. More demonstratively, I have shown in this graph here that for a chosen value, for a chosen set of values of the parameters phi and beta, etc., we have here a clear demonstration that the energy subband degeneracy at the k and k prime points is lifted. So here tau equal 1 corresponds to the k point, tau equal minus 1 to the k prime point. So let's have the solid line for the near the k in the k valley, and the dashed line in the k prime valley. So here you see quite clearly, you see that you have here the solid line and the dashed line, they are separated. So that shows that this degeneracy is lifted. The energy, the flat band energy is no longer flat. It is no longer constant, I should say. And also is shown here in the red, and it's asymmetric. You see, we have here in the two cases, what happens if to the energy subbands, they're no longer conical, but there's a difference which emerges as a result of this external EM field. And so we have brought together a number of cases for different parameters, showing you how you can get, how you can vary the energy gap, you can vary the energy dispersion, you can vary a whole multitude of different things. So that's why we refer to this situation as being very tunable. Okay, so the upshot of what I've said in the previous slides is the following, namely that we have, if we take a cross section for the alpha T3, or maybe even graphene, we have in the absence of the EM field, you have circular, we have a circular dispersion. Here, you see, as I'm emphasizing, we no longer have any necessarily circular dispersion. It becomes asymmetric also. So in this, as a possible application, we've done a number of calculations with regard to transport and other type, also with regard to the impact of an external magnetic field, for example, on the collective excitations, on the plasma excitations, and so forth. But here, in this presentation, we look just briefly at what happens to the case of tunneling. Now let us consider the following, namely, let us suppose we have a sheet of this alpha T3 material, and we apply a bias voltage in one region, and a negative bias voltage in one region and a positive bias in another region. Then there's going to be a step. There's going to be a potential difference. This is what gives rise to this potential step or potential barrier. And we've considered what happens to the transmission coefficient here. And once we have the transmission coefficient, then we can consider or calculate the conductance also. But here, let's consider briefly what happens to the tunneling across this potential barrier. Now, in each region, the potential is constant, so that it's quite straightforward to calculate the wave functions as well as the energies in each of the regions. And here I've shown what the wave function is like on the far side of the potential barrier. It involves this transmission coefficient T. There's going to be, in the region 1, there's going to be an incident and reflected part, which is going to involve a reflection coefficient R. So we have this reflection coefficient R, transmission coefficient T, which both of these guys have to be connected in some way through matching conditions, which I briefly describe on the next slide. So here we have to match the wave functions. Briefly speaking, we have to match the wave functions, and we also have to look at what happens to the wave function itself as you cross the interface. In that case, one finds the following. So these are the boundary conditions. Here I said that you relate the R and the T coefficient, as well as the wave functions, the components of the wave functions, etc. Never mind what this is, but all that this says, well, the key point is that the boundary conditions which we obtain here are quite different from that of graphene, or for the case when we have symmetry, when the system is isotropic. So using that, we find that we can produce polar plots for the case where phi is equal to 0, that is a graphene limit. In that case, you see, you can have perfect transmission, which is called the Klein, referred to as Klein tunneling. Or in some particular cases, you find that the Klein tunneling could be obtained of normal incidence. All right, and so also we have the case where we consider the dice lattice. That is when the phi is equal to pi over 4. Remember in the first part of the talk, I said that we should bear in mind that this value of alpha or phi could be varied. In the case when the alpha is 1, we have this dice lattice. And so these are polar plots of the transmission coefficient for the dice lattice. And so in the previous one, we had for phi or alpha equal to 0, that is for the graphene lattice. And so here we have looked at some density plots of the transmission coefficient, where the lighter the curve means that the higher the probability. So we can adjust the probability of the for perfect incidence for various combinations of the parameters which I mentioned in the talk. And so here again, I've shown them. And so finally is a summary of what I just said. But in principle, what I need to say is the following, namely that this material of alpha T3, the dice lattice, is an emergent material which is gaining a lot of attention, both by experimentalists and theorists. And so I hope that some of the members of the audience would be advised to look more deeply, experimentally, into some of the things which I have reported in this talk. Thank you very much.